Two particles, P and Q, of masses 0.3 kilograms, 0.2 kilograms, respectively, are at rest on a smooth horizontal plane. P is projected at a speed of 4 meters per second and directly towards Q. After P and Q collide, there's a little bit of information that should tell you to use momentum. Q begins to move with a speed of 3. Find the speed of P after the collision. So for this question, all we need to do is find the momentum before and the momentum after. Conservation of momentum says that they have to be the same. Right, so before, the only thing that is moving is the P, and what we know is that the mass is 0.3 multiplied by the velocity, which is 4. All right, remember momentum has a direction, it is a vector, but this is going to the right, and when it hits Q, we're going to definitely expect that Q is moving towards the right, and we would assume P is going to continue moving towards the right as well, because it's heavier and it was going faster. It's a good assumption. If we're wrong, we'll get a negative value. So afterwards, we have two particles in momentum, not just P, we have P and Q. So we don't know the velocity of P, but we still know that its mass stays the same, and we're going to multiply that by the velocity. And the momentum is the combination of the particle P and Q. So afterwards we have 0.2, and it's in the same direction with the velocity, so we can just multiply it by 3. There's an equation we solve. We can, in this case, avoid using a calculator and make the math really easy. Just multiply both sides by 10. Of course, the 10 gets distributed. 10 times 0.3 is 3. 3 fours are 12, so we have 12. 10 times 0.3 is 3. 3 times V. 10 times 0.2 is just 2, times 3 is 6, and hasn't that made our job easy? So take the 6 over, subtract it from 12, we'll get 6, and then divide 6 by 3, and we get 2 meters per second. After the collision, Q moves directly towards the third particle R of mass m, which is at rest on the plane. The two particles Q and R coalesce on impact and move with a speed of 2 meters per second. Find the mass of, well, that's obviously the mass of R, as we read. All right, so the trick here, or is there a trick? It's still just a momentum question, and the two particles are going to collide, and they join, the masses join and become one mass. Where you could go wrong is what we found in the previous part was the velocity of P, but now we're trying to use the velocity of R, which they actually told us in the previous part of the question is 3. So for this one, the momentum before is going to be 0.2 times 3, which of course is going to equal the momentum after. Well, the momentum after is the 0.2 mass of R is going to combine with the mass of Q, and they travel at, we're told, a speed of 2 meters per second. So we just multiply 3 by 0.2, 0.6, expand the brackets, 0.4 plus 2m. So 2m is equal to 0.2, 0.6 minus 0.4, and the mass is 0.1 kilograms. Particle P is projected vertically upwards from horizontal ground. P reaches a maximum height of 45 meters. After reaching the ground, obviously it has fallen back down. P comes to rest without rebounding. Find the speed at which P was projected. So what are we trying to find, and what do we know? We're trying to find the initial speed, which is a velocity, and it's going upwards. So let's call that u, because if we're using constant acceleration, u is the initial velocity, so that's what we're going to start with. The other things that we know, acceleration is going to be -10, and the reason it's -10 is because I made the initial velocity positive. I'm going upwards, and acceleration is going downwards, so it has to be negative. And our displacement, right, we need more information, so we're only going to look at the displacement of 45 when it gets to the top, because what we know is when it gets to the top, the velocity is 0. And once we have these 4 things, we can work out u quite easily. You can look up your formula sheet if you don't know, because it is on there, but we're going to use v squared is u squared plus 2as. V squared is 0 because v is 0. U squared is what we're trying to find, and we have got plus 2 times negative 10 times 45. 2 times 45 is 90, times 10 is 900. Yeah, and it's negative. So we take it over, it becomes positive, and so u is the square root of 900, and the square root of 900 is 30. So it was projected at 30 meters per second. B, find the total time for which the speed of P is at least 10 meters per second. So we need to think for just a little bit here. When it says the speed is at least 10, that means it's 10 or greater. So the minimum that it can be is 10, which means it's going to be faster than 10. When the particle is projected, it's projected at 30, so it's faster than 10, but it slows down. So it's going to get a point in its travel where it travels at less than 10 meters per second. And that's above a line. So what we're trying to find is the time it takes in the initial ascent and the time it takes in the descent. Those two times are going to be the same. So we can find the time for the first stage by saying, well, we know the initial velocity is now 30 meters per second. The final velocity is where it's going to reach 10. We don't know what height that is. It doesn't matter because we know the acceleration is negative 10. If we use that, we can find the time it takes for it to slow down to 10. On the other side of the journey, when it's descending, it's a parabola, so it's going to be the same. It's symmetrical. So we only have to find one side. Which formula uses v, u, a, and t? V is u plus at. So we have got 10 is equal to 30 plus negative 10 times t. So take the 30 over, subtract it from 10, and we get negative 10t is equal to negative 20. So t is 2. But that's half the time, and so we have to double that to get the whole time. The total time is 2 times 2, which is 4 seconds. Question 3, there's a diagram, there's a lot of writing, and it's imperative that you understand what's going on before you start the question. So let's pay a little bit of attention to what's happening here. On our graph, we have a vertical axis which has s, which is meters, and that tells you its displacement. And on the horizontal axis, we have time. So it's a displacement time graph, and we know the gradient of a displacement time graph is the velocity. So it's kind of handy to keep in mind. Let's look at the question. The displacement of a particle moving in a straight line is s meters at time t after leaving a fixed point O. So remember, it's moving in a straight line, so it's obviously going to move away from the origin, and then it's going to come back in the same line because it told us it's a straight line. The particle starts from rest. That means its initial velocity is 0. It passes through the points P, Q, and R at time t is 5, t is 10, and t is 15. So on its journey, at 5 seconds it's at P, at 10 seconds it's at Q, and at 15 seconds it is at R, and then it returns from the journey back to O. The distance OP, OQ, and OR are 50, 150, and 200 meters. All right, so 5 seconds we're at P, but on our graph it's marked as B. That's no problem. We just know that at this point that's 50. And Q, we're told, is 150, and R, we are told, is 200, right? And it's right on 200. The diagram shows a displacement time graph which models the motion of the particle from t is 0 to t is 20. The graph consists of 2 curve segments, AB and CD. So these are the curves, AB and CD, and 2 straight line segments, which are BC and DE. So the straight lines are here, and that's kind of handy because that's very helpful to know. All right, if we've picked up all that information, we can probably answer a question. Find the speed of the particle between t is 5 and t is 10 seconds. Well, that's the BC segment. And so they're asking you for the speed, which is the velocity, and we already have mentioned that the speed is the gradient of the curve, and so all we're looking for is changing the y, changing the x, and we will have the velocity. So armed with this knowledge, the velocity is just the gradient of the line, so we find the change in the vertical, 150 meters minus 50 meters, and we find the change in the horizontal, which is 10 minus 5. And 150 minus 50 is 100, 10 minus 5 is 5, 100 divided by 5 is 20 meters per second. B, find the acceleration of the particle between t0 and t is 5. Okay, remember acceleration is the change in velocity. We don't know the equation of the curve, which is displacement, so we wouldn't differentiate it to get velocity, and we wouldn't differentiate to get acceleration, which they tell us is a constant. But what we do know is that at time equals 0, the velocity is 0, and at time is 5, the velocity is 20, because we just worked that out on the BC segment. Acceleration is the most basic definition, change in velocity over change in time. And given that it's a constant, we can certainly do this. The change in velocity is going to be 20 minus 0, because it ends up at 20, divided by 5 minus 0. And that, of course, turns into 4 meters per second squared. Find the average speed of the particle during its motion. All right, average speed is total distance divided by total time. So all we have to do is know what the total distance is. If you paid careful attention to the graph, you would have noticed that it moved 200 meters away from the origin, and then it came back 200 meters towards the origin. And so the average speed becomes quite easy to work out. It's 200 that it moves away, plus the 200 that it comes back, divided by the time that it takes to do that. 200 plus 200 is 400, divided by 20 is 20. Question 4. In question 3, we hopefully learnt that the more you understand about what the question is giving you, the easier it becomes to answer anything they may ask. And so we want to try and understand what's happening here the best we can before we actually even try to answer any questions. Let's just work out everything that we can about this situation. So the diagram shows a block of mass 10 kilograms. All right, it's got a mass of 10. Straight away that should tell you, oh, the mass is going to produce a weight because of gravity. Weight equals mg. And so we will have 100 newtons of force going straight down from that block. It's suspended below a horizontal ceiling by 2 strings, AC and BC, of lengths 0.8 and 0.6 respectively, attached to fixed points on the ceiling. All right, because they're strings, what we know about strings is they can be under tension, but they can't do any pushing. And so the only way these strings can have any sort of force is if that force is going along the length of the string. Like that. They're my two forces. TA and TB. Let's call them TA, TB, tension A, tension B. We are also told that angle ACB is 90 degrees, and there is a horizontal force of magnitude F acting on the block. We don't know what that is. But the block is in equilibrium, and that tells us that all of these forces are going to add to 0. It also tells us that all the horizontal components will add to 0, and all the vertical components will add to 0. Okay, we're going to need horizontal and vertical components. And how do we do that? Well, we take tension of like B and we break it into a horizontal, and we'll break it into a vertical. But to do that, we need to use sines and coses, right? Whatever this angle is, let's use theta. The opposite is going to be TB sine theta, and the adjacent is going to be TB cos theta, which causes us a little bit of problems, but they may resolve. And for TA, it's going to be the same thing, horizontal and vertical forces. We will have TA cos theta. Oh, we better put an angle in. Let's call it alpha. TA cos alpha makes a lot more sense than theta. And TA sine alpha. Okay, those angles are also in the triangle that they told us is a right angle triangle. By alternate angles on parallel lines, this is going to be alpha up here, and this is going to be theta up there. Okay, if you were really observant, you would have noticed a Pythagorean triad. There's a Pythagorean triad which is 3, 4, 5, the most common one, and that of course has a ratio, a multiple, which is 6, 8, and 10. And of course that can be reduced to 0.6, 0.8, and 1.0, which is just 1. Given that, we would hopefully realize that the length of AB is 1 meter. But let's say you didn't know that. You may have noticed that a right angle triangle, Pythagoras' theorem, is applicable. We can do 0.6 squared plus 0.8 squared, do the square root, and it would turn out to be 1. Okay, why is that useful? Oh, it's a right angle triangle. So we know what the sine of alpha is. The sine of alpha is the opposite, 0.6, over the adjacent, 1. And anything divided by 1 is just itself. So the vertical component for the tension along the line A is just going to be TA times 0.6. The cos of alpha is the adjacent over hypotenuse, which is 0.8 over 1. 0.8 over 1 is just 0.8. So the horizontal component for the tension in A is just going to be TA 0.8. Why did it turn into a Q? And for TB, the same thing applies. The sine of TB, for the sine of theta is going to be 0.8 over 1. And so vertical component is TB 0.8. And the horizontal component is going to be TB 0.6. Okay, that makes everything a whole lot easier about this question. Okay, we can work on the horizontal and vertical forces now. The horizontal forces going left is 0.8 TA, and that's the only force going left. So forces going right is going to be F plus 0.6 TB. Because it's in equilibrium, forces right have to equal forces left. The vertical forces, now the two forces going up, 0.6 TA plus the other force going up, 0.8 TB, tension in B, is going to equal the weight, which is going down. F has no bearing on the weight. Okay, so in the case where F is 20, we can rearrange the first equation that we created into the form of 0.8 TA minus 0.6 TB is equal to 20. We have two simultaneous equations that we can solve. In this case, probably the easiest way is to get the coefficients of TB to be the same. So what do 6 and 8 both go into? 6 and 8 both go into 24. And so let's multiply equation 2, let's call it 2. Equation 2 by 3. And that will turn the 8 into, well, 2.4, which I'm just saying it said was 24. So 3, 6 is 18, which is 1.8 TA plus 2.4 TB is equal to 3 times 100, which is of course 300. For the second one, let's call it equation 3. Everyone can see what's happening. We're going to multiply it by 4, because 6 4s are 24. Why did I choose the coefficient of TB? Because one was positive, one was negative. If we add them together, they will cancel out. And so multiply it by 4. 4 8s are 32. And we're going to subtract 6 4s are 2.4. Well, it's not really 2.4, but you know what I mean. And 4 times 20 is 80. So what we can do is we can add the two equations together, and we'll get, let's start at the back this time. 300 plus 80 is 380. 1.8 plus 3.2 is just 5. So we have 5 TA is 380. 380 divided by 5, put it in a calculator, and we'll get our tension A is 76 newtons is in A. For B, we can use any equation, well, without the F, to find out what B is. I'm just going to rearrange equation number 2. Let's take a couple of steps. 0.8 TB is equal to 100 minus 0.6 times TA, which is 76. And we can use a calculator to work that out. 100 minus 0.6 times 76, all divided by 0.8, turns into 68 newtons. All right, therefore, what do we have to do? Find the tension in your string. Let's just say TA. Hopefully they know what that means. TA is 76 newtons, and TB is equal to 68 newtons. We have to find the greatest value of F for which the block remains in equilibrium in the current position. Okay, so what it means is F is going to get larger and larger and larger. So this force is just going to get bigger and bigger and bigger. And we want to know how large can that force get before the block starts to move, right? After it's going to move, right? And well, since this force is going to get bigger, you think it's going to move in that direction. But there's something that's stopping it from moving directly horizontal, and that's the string TA from the block to A. That's going to only allow this to move in an arc. So if it's going to move horizontally, it's actually going to move in the arc of a circle, which is quite possible if the force remains horizontal. So what's going to happen if it starts moving like that? Well, the tension in B is going to be 0. There's going to be nothing happening in B. And in tension A, it means the vertical component of tension A has to be larger than the weight. So that's the key thing that's going to cause movement here, is when the vertical component of tension A equals the weight. Well, as soon as F gets a little larger, this thing is going to move. Right, so hopefully you remember that the vertical component of tension A was 0.6 TA, and the horizontal component was 0.8 TA, because we're trying to find the force, remember. Okay, so this whole thing is going to just come apart when just after 0.6 in tension A is equal to the weight, which is, so TA is 100 divided by 0.6. Why? Because the force F, now that B is going to have no tension whatsoever when it's about to move, all the weight of the object is in tension A, then the force F is going to equal 0.8 TA. So F is equal to 0.8 times 100 divided by 0.6. So F is going to equal, well, approximately, if we put in a calculator, 133 newtons, more exactly 400 over 3. And that's the answer. A cyclist is riding along a straight horizontal road. The total mass of the cyclist and the bicycle is 70 kilograms. At an instant when the cyclist's speed is 4 meters per second, her acceleration is 3 meters per second squared. There is a constant resistance to motion of magnitude 30. Right, so we're required to find the power developed by the cyclist. We know 2 formulas for power. Power is work on time, or power is force by velocity. Which one will help us in this situation? Well, it would seem force by velocity, because we're told at the instant when the velocity is 4. So that would be a handy thing. All we need to find out is, well, what's the force? And what force are we talking about? It's developed by the cyclist. So we're talking about a driving force. We're talking about the force the cyclist is putting in to move forward. Let's just call it D for driving force. Okay, we know it's accelerating, and we know there's a force forward and a force backwards. So there should be a force equation we can make. The driving force, which is going forwards, minus the 30 newtons, because it's going backwards in the opposite direction, equals the resultant force, which is mass times acceleration. Okay, we're trying to find d, remember. So d is going to equal, the mass is 70, the acceleration at this instance is 0.3, and let's add 30. If we put it into a calculator, we'll get d is 51 newtons, which then tells us what the power is very easy. Power is 51 times 4, force times velocity, which is 204 watts. The cyclist comes to the top of a hill inclined at 5 degrees to the horizontal. The cyclist stops pedaling and freewheels down the hill. There's no more driving force. So the cyclist is no longer supplying any power. Okay. The magnitude of the resistance remains at 30 newtons. And over a distance of d, the speed of the cyclist increases from 6 to 12 meters per second. We're asked to find the change in kinetic energy. The kinetic energy at any point is equal to a half mv squared. But it changes from 6 velocity to 12 velocity, so the change is going to be a half times the mass, which is 70, times the final velocity, which is 12 squared, minus a half times 70 times 6 squared. And if you put that into a calculator, you get 3780, and energy, so it's joules. Use an energy method to find D. Okay, we know that the potential energy is giving energy to the situation because it's going from a higher place to a lower place. So potential energy is saying, hey, here, have some energy. The kinetic energy is taking energy because it's going from a lower speed to a higher speed and it needs energy to do that. Resistance is also there, and the work done by the resistance is energy, and it is always taking energy. So what we know in terms of an equation, there is no driving force, remember, that the potential energy is the only thing that gives energy. So it has to equal the kinetic energy plus the work done by the resistance. Let's just call it R. Okay, if we can put values in for these, we've finished. So potential energy is mgh. And remember, h is vertical. Kinetic energy, we just worked out, 3780. And the work done by the resistance is the amount of the force multiplied by the distance, and the distance is in the direction of the force. So that tells us it's going to be 30 times d. All right, the potential, the mass is 70, gravity is 10, and the height, well, it's not d, it's the vertical height, and the vertical height at an angle of d is the hypotenuse, is going to be d times the sine of the angle, which is 5. All right, and that equals what we have here, 3780 plus 30d. Let's get the d's together. We'll bring the 30d over to the other side, and we'll get 700. Let's put the sine of 5. Let's leave it as sine of 5. We'll minus the 30, factorize d out, and that equals 3780. All right, so we've pretty well finished. We just need to use a calculator. D is 3780 divided by 700 sine of 5 minus 30. Make sure your calculator is in degrees mode, of course. My calculator says 121.9. The front of the paper says give your answers to 3 significant figures. So we will go 1, 2, and the 1 turns into a 2 meters for the distance. Okay, question 6. Let's not panic. Let's try and spend some time understanding what's happening here, because that will be extremely helpful. Two particles P and Q of masses 0.3 and 0.2, they're on the diagram, are attached to the ends of a light inextensible string. The string passes over a smooth pulley at B, which is attached to 2 inclined planes. P lies on a smooth plane AB. Okay, so what that tells us straight away is for P, there's no friction. So there's nothing going against the direction of movement, and we would assume it's going to move down, of course. So there's no friction that's going up in the case of P. 60 degrees to horizontal, that's on the diagram as well. Q lies on a plane BC, which is inclined at 30 degrees. It's on the diagram. The string is taut, so it's got some tension in it, and the particles can move on lines of greater slope to the two planes. All right, if we look at this, 0.3 kilograms is heavier than 0.2. Well, doesn't matter. That doesn't matter too much. What matters is the angle that um, the particles are on, P and Q, because the force that is operating on these, you take the weight, and we resolve the force going down the plane. Oh, it's going to be down to there, and to resolve the force into the plane. They're at right angles, of course. So that force down the plane is directly proportional to the acceleration. And on Q, if we take the weight and we resolve it in down the plane and into the plane, the force down the plane for Q is directly proportional to the acceleration. Which acceleration would we expect to be higher? Well, the 0.3 for sure. The vector's longer for the weight. The weight is 3. The vector for the Q is only 2 newtons, right? Let's write that in there. So the weight is 2 newtons here. The weight is 3 newtons here. But when that gets resolved, the force going down from P is got to be larger than the force going down from Q. And the weight is what, if there was no string, that's the thing that is going to move the particles. And that's going to be directly proportional to the acceleration. With all of that information, we know, oh, well, P is going to fall faster than Q is going to fall, which means P is going to pull Q down. All right, that's put tension in the string. Now, tension always works the same way. If a string is under tension, it's pulling back on both of the objects. So for P, it's pulling up, and for Q, the tension is pulling down. We'll write that. Tension, and then the weight components are the other forces. Right, because there's no friction, there are no other forces, and so we can probably solve the question. Let's have a look. Part A, it's given that the plane BC is smooth. All right, that's really nice. There's no friction on BC, and the particles are released from rest. Find the tension in the string and the magnitude of the acceleration. Okay, so to do that, we're just going to create a force equation for each of the objects and each of the particles, and that should do the job for us. So if we look at the 3 newtons, we know that 60 degrees is also there, and that means that the force down is going to be 3 sine 60. And the force up is the tension. For the 0.2 kilograms, it's at 30 degrees. So 30 degrees is there, which means the component of the force going down the plane is 2 sine 30. And we have 2 forces going down for Q, T and 2 sine 30. All right, what they're going to add to for both cases is the resultant force, which of course is mass times acceleration. And the resultant force is different for both because the masses are different, but the acceleration will be the same because they're moving at the same speed. So putting those few minutes in to work out what's happening really helps us create the force equations. For P, we have got the force going down, which is 3 sine 60, minus the tension, which is going up, is equal to the resultant force, which is the mass times acceleration, 0.3a. For Q, we have got both forces acting in the same direction. So we've got 2 sine 30 plus t, because tension is going down as well, is equal to the acceleration, which is in this case 0.2a. Right, these are really nice equations because we have a minus t and a plus t. So if we just add the 2 equations, we'll eliminate the variable t and we're just left with the acceleration. The sine of 60 is root 3 on 2, and the sine of 30 is a half. All right, so when we add that together, we will get 3 root 3 on 2, plus a half of 2 is just 1, and that equals 0.5a, or 0.5a is a half of a. We'll multiply both sides by 2. Let's add these fractions together. So let's take the 2 and multiply it on the other side, and let's add the fractions. We'll get 3 root 3 plus 2 on 2. Right, you can see why I did that now. And so the acceleration is equal to 3 root 3 plus 2. We probably need a number. Okay, so my calculator is saying that this is 7.19615. From the paper says round to 3 significant figures, so 7.196 turns into 7.20. 7.20 meters second squared. All right, let's use the equation for Q to work out the tension, because we just worked out 2 sine 30 is just 1. So we have the tension is equal to 0.2 times what we just worked out. Use the exact value, of course, and minus 2 sine 30, which is just minus 1. All right, let's use the value that's in our calculator and multiply it by 0.2 and then subtract 1, and we will get 0.4392. Right, rounding to 3 significant figures, 0.439 newtons. On to part B. It is given instead that the plane BC is rough, so now there's friction. A force of magnitude 3 newtons is applied to Q directly up the plane along the line of greatest slope. Find the least value of the coefficient of friction between Q and the plane BC for which the particles remain at rest. Well, let's try to figure something out. We know that this particle sitting here is Q, right? There's now a force up the plane which is 3 newtons. The weight component is still going down the plane, and tension is still going down the plane. It's tension and weight. It's the component of the weight. And there's also friction now. And which way is the friction? Is it going down or up? Great question. Like, which way is it trying to move? Because friction is always opposite the direction of movement, and we don't know. Where is the friction? So we could guess. I guess we could just have a guess. But maybe we should be a little smarter than just guessing things. Let's look at the other particle, which is on the steeper surface, right? It's still on a smooth surface, so it still has its weight component going down and its tension going up. There's no other force acting on it. The tension is going up. The weight component is going down. There's no friction. It's still a smooth surface. And we're told that it's in equilibrium, and we're trying to find something related to equilibrium. That tells us straight away that those two forces have to be equal to each other. So for Q, we're not really sure which way the friction goes, but for P, we know that the tension is going to equal the weight. Okay, that is probably going to help us unravel what's happening with Q and which way the friction is going. So for P, we are going to have the weight component, which is mg 0.3 times 10 is 3 newtons. Sine of 60 is equal to t. Yes, that's not too bad. Oh yeah, that's so the sine of 60 is still root 3 on 2. So let's actually get an approximate value for that instead of the exact value, so we can see what's happening. All right, so the tension turns out to be 2.598. 2.59 is going to turn to 60 if we round it to 3 significant figures. Newtons. Right, now because it's in equilibrium at P, the tension has to be that for it to be in equilibrium. There are no other forces involved. And that tension is the same all the way through the string, and so the tension on Q is going to be around about 2.6. It's not exactly, but very close. So what was the component of the weight for Q? This is just ending up all over the place here. The weight was mg, so it was 2 sine of 30, you may remember. And sine 30 is a half, so it turns into 1 newton. Okay, so if we consider that the tension is 2.6 and the weight is 1 and they're in the same direction, we add those together, we're going to get 3.6 newtons going down, and we're having 3 newtons going up. which means that the friction, it will want to move down. That's what it means. It is going to slide down because the force from the tension and the weight is larger than the force going up the slope. That means the friction has to be going up the slope. Right, Q is in equilibrium, nothing's moving, remember. That means all those forces have to cancel each other out, or they all have to add to zero. Well, we can do the add to, we can say cancel each other out. I like that version better. So the tension, which is going down, we have around about 2.6. I'm always going to use the exact value on my calculator. Plus the weight going down, which is 1, has to equal the friction force going up, which is mu times the normal. Let's actually change the friction into mu times the normal now, which we normally call R, plus 3. And so that should really help us work out what mu is, because we can work out what R is. All right, so if we add the 1 to the 2.6, we get 3.6. If we subtract the 3, we'll get 0.6. Use exact values. And that is going to equal coefficient of friction times R. R is the weight, which is 2. 0.2 times 10 times the cos of 30. Cos of 30 is root 3 on 2. Oh, so that's going to be root 3. So mu is equal to 0.6 divided by root 3. Okay, we can remember we're using the exact value that was in my calculator. And I get the coefficient of friction is 0.3452, so we round it to 0.345. Question 7. A particle P moves in a straight line through a point O. Okay, the velocity V at P at any time after passing O is given by this. Okay, so O is origin. The velocity is some equation based on T, time, and there are 2 unknown constants, B and C. B and C are positive constants. At time equals 5, the velocity of P is 0. Okay, velocity is 0 at T is 5. And its acceleration is something. We have an acceleration, not minus 13 on 12. Show that B equals 9 and the value of C. And find the value of C, sorry. All right, we're given 2 things. One is the velocity at 5, and one is the acceleration at 5. So I would imagine we need 2 equations to find out what B and C are. And we need velocity and we need acceleration. All right, so the first thing we're going to do is just differentiate. Velocity is 9 on 4 plus, let's write this a little nicer. We'll take it so we can differentiate it. That's all I'm trying to do. T plus 1 to the minus 2 minus c t squared. All right, so that tells me the acceleration is equal to the differentiation of the velocity. 9 on 4 disappears, the minus 2 comes out, differentiate the t plus 1, you get 1. So we end up with minus 2b over t plus 1. Subtract 1, we get negative 3. And for ct squared, the 2 comes down, so it's going to be 2 times c t, subtract 1 from 2, and we just get 1. And that's it. Differentiate velocity, you get acceleration. So we have 2 equations, and we know that when t is 5, velocity is 0, and acceleration is minus 13 on 12. So we're going to put those into the equations and see if we can solve them. So let's do the velocity. 0 is equal to 9 on 4 plus, let's put it back like this, b over 5 plus 1 squared minus c times 5 squared. All right, hopefully we can simplify this. 5 plus 1 squared is 36. So we have b on 36. We have 9 on 4, still equals 0. And over here we have minus 25c. 5 5s are 25. Okay, I've mentioned before in class that I like it when I get rid of fractions. It just makes my whole life easier. So if we multiply both sides of this equation by 36, we're going to get rid of the fractions, right? So 9 on 4 times 36, well, 4 goes into 36 9 times, so that just becomes 9 times 9, which is 81. and of course 9 times, so 36 times 0 is 0. 36 times b on 36 is just b, and 36 times 25, might need a calculator for this one, is 900. Okay, so that was the velocity, and that equation looks a lot nicer than an equation with fractions. So we will try the acceleration equation and see if we can't do something similar. Okay, we have the acceleration is negative 13 on 12 when time equals 5. All right, let's again turn it back into fractions. Hopefully we can do something to fix our problems later. Minus 2b divided by 5 plus 1, and this time it is cubed. We're going to subtract 2 times c times just 5. Okay, 5 plus 1 is 6, and 6 cubed is 216. All right, so let's multiply everything by 216 because that's going to get rid of that fraction. So 216, let's divide, times it by 13 on 12. So divide it by 12, we get 18. Times it by 13, and we get 234. So we have negative 234, and the whole reason we did it was to make this one look nice. 2b, and we're going to have 2 5s are 10. Times 216 is going to be 2160c. So it didn't turn out to be too hard. We could multiply both sides by -1 and get rid of that minus sign. It's kind of easy for me to do. Let's turn that into a plus. So that's good, and we've got a nice equation. Right, so we have two equations, two unknowns. In the velocity equation, there's a single b. We can divide both sides of this equation by 2, and that'll give us a single b as well. So 117 is equal to b plus 216, so divide by 2, 1080c. All right, so this is our acceleration equation. Let's just put that there to remind us. And our velocity equation is what we want to use elimination with. The velocity equation is, let's take the 81 over and get minus 81 is equal to b minus 900c. Okay, we can make that look a whole lot nicer if we actually made everything multiplied by -1 on both sides. Because now we just add the two equations and we will eliminate the variable b. So 81 plus 117 is 198 is equal to 1980c. Well, that's handy. C has obviously got to be 0.1. Divide by 10, 1/10. Good job. To find b, I'm going to use the velocity equation, this one. And we have a minus b there. So I'm going to throw that onto the other side to make it positive b, and I'm going to take the 81 and bring it over to make it negative b. So we have 900 times 0.1, which is 90, and minus 81, which means that b has to be 9. Because 90 minus 81 is 9, and we have our two answers. B is 9, and C is 0.1. B, given that the velocity of p is 0 only at t equals 5, find the distance traveled in the first 10 seconds. All right, if we had a velocity time equation, which is kind of important that we understand this, when time is 5, the velocity is 0. So velocity time, we're going to be 0 at that point, which means kind of the only way we can do that is part of the equation is above, part is below. It's not really the only way that we could do that. You could have like a turning point there, but that would be a special case if there was a turning point there. Well, we're trying to find the distance traveled, right? And if one part is above and one part is below in the first 10 seconds, that's 5, and then we have a 10 out here. We really want to break this up because it's integration of velocity, right? Integration area under the curve. We want to break it up into two parts, just in case one of them is negative. If we try and do the whole thing and one of them is negative, that's going to give us the wrong answer. So given we don't know exactly what the equation looks like, but we know we should integrate the velocity, and we should do it from 0 to 5, and we should also do it from 5 to 10 and see what we get. Right, if we grab our velocity equation and put in the b and c that we know velocity is 9 on 4 plus b is 9 over t plus 1 squared and minus 0.1 is 1 on 10 t squared. Right, because we're integrating, we want to make that look maybe a little bit nicer. Oh, we're not going to make it look a whole lot nicer, just a little bit. 9. Why is that 9 not working? T plus 1, negative 2, minus 1 on 10 t squared. Okay, we definitely need the integration, so let's do displacement is equal to 9 on 4t. Okay, what happens when we're doing chain rule? T plus 1 stays the same. The minus 1, we're going to add 1. Sorry, the minus 2, we're going to add 1, and we'll get negative 1. The negative 1 would have come and made the 9 negative, so we have to start with a negative, and the t would differentiate to put a 1 out the front, so that doesn't do anything. We don't have to worry about it. And the t squared would come from t cubed. We have to divide by 3. So that's going to be 1 on 30. Right, so we're going to integrate from 0 to 5 the velocity function of t with respect to t. And that will equal 9 on 4 t minus 9 over t plus 1 minus, what will we do? 1 on 30 t cubed, 0 to 5. Okay, generally on these exams, they like it when you substitute values in to show you know what you're doing. So we should do that. 5 nines, 45 on 4 minus 5 plus 1 is 6, 9 on 6 minus t cubed, 5 5 is 25, 5 times 25, 125 on 30, and we're going to subtract 0. 0 plus 1 is just 1, 9 divided minus 9, and 0. Okay, they're actually useful, the 0 and the 5. Well, 5 is in the other one as well. Of course, we're going to integrate from 5 to 10. So we should work each of these out. Okay, so this will equal 67 on 12, which is going to save us some work later, minus negative 9. That just turns into plus 9. And if we complete the area for this one, we add 9, we get 14.583 or 175 on 12. All right, the second stage is we're integrating from 5 to 10 of the velocity function with regard to time. It's going to equal exactly what we had up the top, 9 on 4 t minus 9 over t plus 1 minus 1 on 30 t cubed, but this time we're going from 5 to 10. All right, we already know what the 5 is when you substitute it. We just have to work out what the 10 is. We end up 90 for the first term, 90 on 4, minus 9 on 11, minus 1,000 on 30. And for the second term, I think we can just go straight to what we got when we put in the 5, which was 67 over 12. All right, put it into a calculator, and I get minus 769 divided by 66. Yeah, it's a terrible number. And we're going to subtract, of course, the 67 on 12. Thank God for calculators. Gives us, what does it give us? Again, another problematic number. Minus 2,275 divided by 132. Right, so that negative area shouldn't worry us because we were sort of expecting that one area would be above the axis and one would be below. And we want to add the two absolute values of the area together to get the distance. So for us, the distance is equal to the first area, 175 over 12, but not plus. We're going, sorry, not minus, we're going to plus. 2,275, pen is not working too well. 132. Why pen? Put in a calculator and we get 350 on 11, which is approximately equal to 31.8181. Let's round that to three significant figures. 31.8 meters. And we're finished.